Hello everyone. Welcome to the presentation series We Shall Overcome, conducted by the Physics Department of Sacred College, Thevara. We are really honored to have Dr. Pius Augustine as our faculty advisor. I would like to thank Dr. Pius Augustine for giving us such a wonderful opportunity and helping us to come up with our maximum potential. Michael Jordan says, talent wins games, but teamwork and intelligence win championship. Hereby are introduced my group members Rose Mathew, Jency Johnson, Anagha Paul, Tessa Antony, Amala Varghese, and myself, Ansu Martin. The topic of our presentation is radiation. In simple words, it can be described as a transfer of energy in the form of electromagnetic waves. On the basis of energy, radiation can be classified as ionizing radiation and non ionizing radiation. Further, they can be classified as electromagnetic radiation, particle radiation, gravitational radiation, etc. Radiation finds application in medicine, communication, agriculture, carbon dating, space exploration, and many more. But exposure to high levels of radiation adversely affect our health, leading to skin burns, genetic disorders, and even cancer. Now, let us have a look on the contents of the presentation. The contents of the presentation include thermal radiation, blackbody radiation, Kirchhoff law and its applications, Wien's displacement law, Rayleigh-Jeans law, UV catastrophe, and Planck's radiation law. Now, let me introduce myself. I am Ansu Martin and I will be dealing with the modes of heat transfer, thermal radiation, rate of radiation, importance of radiation, some basic definitions, Brewer's theory of heat exchange, application of heat radiation, and uniform temperature enclosure. What are the different modes of heat transfer? They are conduction, convection, and radiation. Now, let us discuss about conduction. Thermal conduction is the transfer of internal energy by microscopic collision of the particles and movement of electrons within the body. It usually occurs in solids. For example, while holding one end of the spoon in fire, the other end also gets heated up. Now, let us discuss about convection. Convection is the mode of heat transfer that usually occurs in fluids, that is, in liquids and gases. Here, the bulk movement of the molecules within the fluid occurs. Let us see an example. While boiling water, when the fluid is heated, the lower layer gets heated up, which becomes less dense and expands. Hence, an empty space will be created, which is replaced by the colder, dense fluid layer. This process repeats until uniform temperature is obtained. So, now we have seen that both conduction and convection requires an intervening medium. But how is radiation different from conduction and convection? Radiation is the mode of heat transfer in which energy is transmitted in the form of electromagnetic waves. Radiation occurs in the absence of any intervening medium. Is heat transfer possible through vacuum? This was the question which led to the formation of a new concept called radiation. For finding this, an evacuated chamber was taken and its inner wall was maintained at a temperature Tc. Inside this, an hot object of temperature Th was placed. Variation in these two temperatures with time was noted. As you can see in the graph, it was noted that Th keeps on decreasing and Tc keeps on increasing until the two temperatures are equal. Hence, it was proved that the transfer of heat is possible even through vacuum. What is thermal radiation? It is the transfer of heat from a hot body to a cold body. It occurs whenever the temperature of a body is greater than the absolute zero of temperature. One of the best examples of thermal radiation is the radiation of heat from sun. The intervening space between the sun and the earth is vacuum, but still we receive energy from the sun. This occurs through the process of thermal radiation. We have seen that we are receiving radiation from sun. Now, let me ask a question. What is the rate at which energy meets an object? This can be calculated using the Stephen Boltzmann law. The equation delta Q divided by delta T is equal to epsilon sigma A T raised to 4 gives the rate of heat radiation, where delta Q is the change in energy, delta T is the change in temperature, epsilon is the emissivity, sigma the Boltzmann constant, and its value is equal to 5.67 into 10 raised to minus 8 volt per meter square per Kelvin raised to 4. A is the area of the surface emitting radiation and T is the temperature of the object. Is radiation really important? Can there be an existence of life without radiation? The answer for this question is no. Human body is made up of biological cells. For existence, our body should have a certain temperature which is maintained by the heat from the sun. How do plants make food? The chlorophyll pigment in the plants absorb light from the sun and combine with carbon dioxide to make food and release oxygen. The absorbed light is nothing else but the thermal radiation. Hence, we get food and oxygen. How is thermal radiation related to water? Our oceans and rivers contain a lot of water, but it cannot be directly consumed. Heat causes water in the oceans to evaporate, leading to the cloud formation and which in turn fall as rain. Hence, we get water that can be consumed. Now, let us discuss about some of the properties of thermal radiation. Thermal radiation includes the UV, visible, and IR region of the electromagnetic spectrum. The wavelength ranges from zero point 0.1 micrometer to 100 micrometer. Of these, zero point 0.1 to zero point 0.4 micrometer is the UV region, zero point 0.4 to 0.76 is the visible region, and 0.76 to 100 micrometer is the IR region. It is electromagnetic in nature and travels in a straight line. It also exhibits all the properties of light. It obeys inverse square law. It exhibits the properties of reflection, refraction, interference, polarization, and diffraction. Now, let us discuss some important definitions. Before that, you must remember the energy emitted from a body is not of a single wavelength but includes a group of wavelengths. What is total energy density? It is the total energy of for all wavelengths per unit volume. It is represented as mu. The unit of energy is joule and that of volume as meter cube. Hence, total energy density takes the unit joule per meter cube. What is spectral energy density? It is the energy per unit volume per unit range of the wavelength. Here, we consider a single wavelength. Total energy density mu and the spectral energy density mu lambda can be related as mu is equal to integral 0 to infinity mu lambda d lambda, where mu lambda d lambda is the energy per unit volume in the wavelength range lambda to lambda plus d lambda. Total emissive power. Total emissive power is total radiant energy emitted for all wavelengths per second per unit surface area. The unit of energy is joule, that of area is meter square, and of time is second. Thus, the unit of total emissive power is joule per meter square per second. Spectral emissive power. It is the radiant energy per unit wavelength per second per unit surface area. Total emissive power E can be related to the spectral emissive power E lambda as E is equal to integral 0 to infinity E lambda d lambda, where E lambda d lambda is the radiant energy per unit surface area per second in the wavelength range lambda to lambda plus d lambda. Spectral absorptivity, represented as A lambda. It is the fraction of incident radiation absorbed by a body for a wavelength. Since It is a fraction, it does not have any unit. Relative emittance. It is the ratio of emittance of a body to that of a black body. Since it is a ratio, it does not have any unit. Previous theory of heat exchange. Prior to 1792, people thought that cold body emit cold radiation and hot body emit hot radiation. But Pierre Prevost said that there is neither hot radiations nor cold radiations. He said that every material body absorbs and radiates heat above absolute zero of temperature, and this process of heat exchange depends on the temperature and the nature of the surface. When we are standing near fire, we feel warm because we are receiving more energy from fire. Similarly, when we are standing near an ice block, we feel cold because our body loses more heat than it receives from the surroundings. Now, let us have a look on certain applications of heat radiation. White clothes are preferred in summer and dark clothes in winter. When heat radiation falls on white cloth, they are reflected back. Dark clothes in winter will absorb the radiations falling on them and will keep the body warm. Cooking utensils are blackened at the bottom and polished on the upper surface. Black surface will absorb the wall of the heat from the furnace, and upper surface will not allow the heat inside the utensil to flow out. Polished reflectors are used in electric heaters to reject maximum heat in the room. Thermocouple junction exposed to light is blackened to absorb maximum quantity of heat. Uniform temperature enclosure. Generally, the quantity and quality of radiation depends on temperature and the nature of the surface. If we consider a non-conducting enclosure at constant temperature, the quantity and quality of radiation inside it depends on the temperature and is entirely independent of the nature of the wall and the nature of the bodies present inside it. Such an enclosure is called uniform temperature enclosure. So that's the end of my topic. And now I welcome Rose Mathew to deal with black body radiation. So over to Rose.
Thank you, Ansu. So far, we have come across the basic definitions in radiation. Now, I'll be dealing with black body radiation, and black body in practice. Firstly, let's see what is a black body. A body which completely absorbs all the incident radiations of any wavelength falling on it is known as a black body. Hence, a black body neither reflects nor transmits any radiation. It is for the same reason it appears black irrespective of the wavelength of the incident radiation. Example of a black body are Van der black and carbon black. Do you know what is this Van der black and carbon black? Van der black is a material which is made from a carbon nanotube, and it is considered as the blackest black in existence. It absorbs 99.96% of the incident radiation. In the similar manner, carbon black is also a material which absorbs 99% of the incident radiation. This figure represents the image of a black body which absorbs radiations falling on it. Moving on, we shall discuss about black body radiation and its temperature dependence. When a perfect black body is heated to a suitable high temperature, it emits radiation of all possible wavelength, and this radiation is considered as a black body radiation. So, when will it start emitting radiation? When the temperature of the black body is increased as compared to its surrounding, then black body will emit radiation, and it will emit radiations of all wavelength. So we can say that a perfect black body, when it is at high temperature, it will emit radiations, and when it is at lower temperature, it will absorb radiation. Now let's look at the examples. When we sit in sun, we feel warmth. Why is it so? This is because of the process of radiation. So, sun is an example of black body which emits radiation of all wavelength. And also, a familiar example for all of us is a burning gas stove. It is also an example of black body radiation. Now, let's see how is this black body and the temperature are dependent. When the temperature of the black body is increased as compared to its surrounding, then it will start radiating all the wavelength. That is, black body radiations are independent of the nature of the substance and nature of the walls of the enclosure, but depends only on the temperature of the substance. Here, the point to be noted is that black body radiation does not depend on the nature of the substance. It depends only on the temperature of the substance. Now, we will discuss about black body in practice. A surface coated with lamp black or platinum black is an example of a perfect black body. A 100% perfect black body is just a hypothetical one. So, a surface which absorbs 96 to 98% of the incident radiation can be constructed. This is made possible by two different ways. So, let's check it out. First method is Wien's black body. Just have a close look at the figure. This Wien's black body consists of a hollow cylindrical chamber C, which is made out of brass or platinum, having heating coils of thin platinum wire H wound over it. As you can see, the cylinder is protected by coaxial porcelain tubes P. When a suitable current is passed through the coil, the cylinder is heated to a desired temperature, and as you can see, the inner surface of the chamber C, it is painted black so that it reaches an equilibrium position in a smaller time. So the radiations from the cylinder is limited by the black and concave diaphragms. The radiation emerge out of the hole O finally, and we can say that this hole O will act as the black body radiator. That's it about Wien's black body. Now we will discuss about Ferri's black body. Ferri's black body is generally used for accurate experimental works. From the figure, we can see that it is a hollow sphere and it is having a small opening O at one end, and just opposite to this opening there is a conical projection. What is the use of this conical projection? This conical projection prevents direct reflection of any radiation. So the radiation entering the opening suffers multiple reflection at the inner walls. Eventually, what happens to this radiation? After a few reflection, almost all the radiations get absorbed. So when the body is heated, it becomes a source of thermal radiation. The radiation from the constant temperature enclosure depends only on the temperature of the enclosure, as we have discussed earlier. It does not depend on the nature of the material. So that's all about Ferri's black body. So I hope this topic is clear for you. So far we have discussed black body and its temperature dependence, and black body in practice. Now I invite Jency to continue with Kirchhoff's law of radiation and its applications.
Thank you, Rose. And hi, everyone. Now we are going to learn about Kirchhoff's law of radiation and its application. Before going to that, we have to understand certain terms. The first one is MC power. The MC power is denoted by small e lambda. We all know that every body at a particular temperature emits radiation, and this property of the body is the emissive power, and it is defined as the energy emitted per second per unit surface area of the body. And what is the amount of radiation emitted per unit time? Yes, it is the power. So, we can define the MC power as the power emitted by the surface per unit area. So, what is the power emitted by surface per unit area? Yeah, it is the intensity. So, finally, we can define the MC power as the intensity of emitted radiation at a point on the surface. So, the MC power is a intensity. Next one is absorptive power and is denoted by small a lambda. And in the case of an absorptive power, it is a ratio. So it is a unitless quantity. And the absorptive power is defined as the ratio of amount of energy absorbed in a given time by the surface to the amount of energy incident on the surface in the same time. For more clarification, let us consider two bodies. One is a normal body and another one is a black body. Both are at the same temperature and identical in their shape and size. If Qi is the amount of energy incident on the surface of the normal body, it will absorb only a small part from Qi, and that is Qa. But in the case of a black body, it will absorb all the radiation which incident on its surface. So, we can define the absorptive power or absorptivity A lambda as the ratio of amount of energy absorbed by the normal body to the amount of energy absorbed by the black body. We know that the amount of energy absorbed by the black body is equal to the amount of energy incident on the surface of the black body. So, the absorptive power A lambda will be equal to Qa, that is the amount of energy absorbed by the body, by Qi, that is the amount of energy incident on its surface. Next one is emissivity. In the case of an emissivity, it is also a ratio. So it is a unitless quantity and it is defined as the ratio of emissive power of a body at a given temperature to the emissive power of a black body at the same temperature. In the case of an emissivity and absorptivity, both are ratio and they are unitless quantity. But in the case of an emissive power, it is a intensity. So it has a unit. By understanding these three terms, we can go to Kirchhoff's law of radiation. It states that the ratio of emissive power to the absorptive power for a given wavelength at a given temperature is same for all bodies and is equal to the emissive power of a perfectly black body at that temperature. And the equation is given as capital E lambda is equal to small e lambda, that is the emissive power, divided by small a lambda, that is the absorptive power. If we consider this equation in the case of a black body, we know that for a black body the absorptive power A lambda is 1 because the amount of energy incident on the surface of a black body is equal to the amount of energy absorbed by the black body. So the equation will become capital E lambda is equal to small e lambda, which means for a black body the emissive power will be maximum and it is denoted as capital E lambda. And if we rearrange this equation, that is the small a lambda is equal to small e lambda, which means for a body emitting and absorbing thermal radiation in thermal equilibrium, the emissivity is equal to its absorptivity. That is, the absorptivity for a radiation of certain wavelength will be equal to the emissivity corresponding to the radiation of same wavelength, which means if the body's absorptivity increases, the emissivity also increases. If the body's emissivity decreases, the absorptivity also decreases. So, the Kirchhoff law of radiation concludes that the good absorber is a good emitter.
which means if a body absorbs radiation of a particular wavelength strongly, it also emits the same radiation strongly. Now, let's see some applications of Kirchhoff law in our day-to-day life. A sodium vapor which emits two yellow lines strongly is also a good absorber of light of these two wavelengths. When a green glass heated to high temperature, it glows red, and a red glass heated in a furnace, when taken out, it appears green. When it is cooled down, it appears red because it absorbs green light strongly. When red glass is heated, it emits green light strongly. This is because red and green are complementary colors. At ordinary temperature, a green glass appears green because it emits green color and absorbs red color strongly. According to Kirchhoff's law, this green glass on heating must emit the red color which is absorbed strongly. Similarly, when red glass is heated to a high temperature, it will glow with the green light. In desert, the days are hot and nights are cold. This is because in desert the sand is rough black, so it is a good absorber. Hence, in the desert, at the daytime, the sand will absorb all the radiation from the sun and it makes the days very hot. In accordance with the Kirchhoff law, good absorber is a good emitter. So at the night time, the sand will emit this radiation and which make the night so cool. And this is why the days are hot and nights are cold in desert. And that's all about the Kirchhoff law and its application. The next topic will take by Anagha. So over to Anagha.
Thanks, Jency. Hi all, I'm Anagha Paul. When I was little, I used to gaze upon the night sky. You all might have had moments like this. Stars always fascinated me and still it does. Hey, do you want to know some fun facts about stars? The largest stars are called hypergiants. One absurdly large one is called VY Canis Majoris. If you stacked about 1420 of our suns on top of each other, you would have the diameter of VY Canis Majoris. The surface temperature of a sun is about 5778 Kelvin. Our sun is a dwarf star, precisely saying a yellow dwarf. Cool, right? Have you ever wondered how we are able to know so many things about stars even when we haven't been able to approach one? Even our nearest star, that is the sun, seems far beyond our reach. The answer is that, for example, our DNA contains the coded information about our physical and biological traits. Similarly, the electromagnetic spectrum that a star emits contains information about its traits or properties. The difference is that our traits are the result of our DNA, while the electromagnetic spectrum is the result of a star's properties. You may be wondering why am I discussing about stars instead of the laws given in the current slide. Well, these laws help us to calculate certain properties of a black body. As by now, you may know that stars are examples for a black body. In turn, these laws are useful in finding or learning about stars. So, in this section, we are going to learn how to calculate the temperature of a star. The stars exist in a wide range of colors: red, orange, yellow, green, white, and blue. At the end of this section, you would be also able to identify which one is the hottest just by looking at its color. Now, imagine that you are heating an iron rod. First, iron turns into red, and as the temperature rises, it glows and turns into orange, yellow, blue, respectively. If we go on heating the rod, it turns into white light, which includes all visible wavelengths. We know that the red light has higher wavelength while the blue has shorter wavelength. So from this experiment, it is seen that as temperature increases, the color moves towards shorter wavelengths, or we can say that the temperature of an object is inversely proportional to its wavelength. This is the concept of the Wien's displacement law. By now, you would know that black bodies are the objects that absorb and emit radiations of all wavelengths. But the energy distribution is not homogeneous. The graph given here describes this. The y-axis here is the intensity or number of photons emitted. The x-axis is the wavelength of radiation emitted. As we can see that the most of the photons are emitted in the wavelength lambda max, or we can say that the energy radiated is maximum at a particular wavelength, that is lambda max or lambda m. This wavelength is called dominating wavelength, and the color of the object would be the color corresponding to this wavelength. So if lambda m is in the red region of visible light spectra, then the object would seem red. We can also see that the lambda m displaces towards shorter wavelengths as the temperature is increased. So the Wien's displacement law shows that the dominating wavelength is inversely proportional to the temperature. We will discuss more about this graph in Lammer and Pringsheim experiment. Now, let's see the statement for Wien's displacement law. The law states that the product of wavelength corresponding to maximum energy, that is lambda max, and absolute temperature, capital T, is a constant. That is, lambda max into T is a constant. The expression for Wien's displacement law is lambda m or lambda max is equal to b by t. Here, lambda max is the peak of the wavelength. B is the Wien's displacement constant, which is 2.9 into 10 raised to minus 3 meter Kelvin for a black body, and capital T is the absolute temperature in Kelvin. The next law that we are going to learn would help us to find the luminosity of a star. Luminosity is the measure of total amount of energy radiated by a star per second. It is therefore the power output of a star. It can also be simply said as the brightness of a star, and it is measured in terms of watts. But we cannot determine the brightness of a star from Earth. Distance is a factor for brightness in this case. Stars that are closer to Earth but fainter could appear brighter than far more luminous ones that are far away. So we have to factor out the distance in order to find its true brightness. So the law that helps us to find the luminosity of a star is Stefan-Boltzmann's law. The law states that the rate of radiant energy per unit area of a black body is directly proportional to the fourth power in Kelvin temperature. For a body with temperature capital T, the Stefan-Boltzmann equation can be written as capital E is equal to small letter e sigma T raised to 4. Here capital E is equal to Q by A into T, where Q is the energy radiated, A is the surface area, and T is the time. The constant sigma here is Stefan's constant, and it has value 5.67 into 10 raised to minus 8. Small letter e here is emissivity of an object. The point to be noted is that the emissivity of a black body is 0, and for others it ranges from 0 to 1. So taking the emissivity of a black body into consideration, we can write the Stefan-Boltzmann's law for a black body as capital E is equal to sigma T raised to 4. So now we can try to answer our question. Luminosity is the electromagnetic radiation that a star emits. It can be simply said as the rate of radiant energy. Therefore, the equation for luminosity will become L is equal to Q by T, which is equal to sigma A into T raised to 4. As we can consider this star as a sphere, then the equation for luminosity will become L is equal to 4 pi r square sigma T raised to 4. An object that emits radiation well will also absorb radiation well. The Stefan's law don't take this absorption into consideration. So we have to rewrite this equation. In the case where a body at absolute temperature T is surrounded by another body at absolute temperature T0, then the power is radiated and absorbed. Then the power radiated would be equal to E sigma A into T raised to 4. Power absorbed will be equal to E sigma A into T0 raised to 4. Then the net power radiated will be equal to E sigma A into T raised to 4 minus T0 raised to 4. This is the complete Stefan-Boltzmann's law. In the case of a black body, it will be E A T raised to 4 minus T0 raised to 4. So next, we are going to study about the distribution of energy in black body spectrum. Lammer and Pringsheim investigated the distribution of energy among the radiation emitted by a black body at different temperatures. This is their experimental arrangement. The black body consists of a carbon tube heated electrically. Its temperature is measured using thermocouple. Radiation from the black body is made to pass through a narrow slit and get reflected from the concave mirror M1. After reflection, the beam will be parallel. The beam is dispersed by a rock salt or fluorospar prism P mounted on the spectrometer table. The dispersed beam after reflection from the concave mirror M2 gets focused on the bolometer placed behind the slit S2. Reflection in the galvanometer of the bolometer is the measure of the intensity of each line. By rotating the present table, deflection in the galvanometer is noted for various parts of the spectrum. A curve is drawn between intensity and wavelength. So, this is the graph obtained. So, the curves for different temperature is given in the graph. The energy is not uniformly distributed in the radiation spectrum for a given temperature. The intensity increases with the increase in wavelength, and at lambda max, its value is maximum. With further increase in wavelength, intensity of heat radiation decreases. Then we can see that as temperature increases, lambda max displaces towards shorter wavelength. That is, lambda max into T is a constant and Wien's displacement law is proved. The area under each curve represents the total energy emitted by the body at that particular temperature. Or we can say that area is directly proportional to the fourth power of temperature of the body. That is, capital E is directly proportional to T raised to 4. This represents Stefan Boltzmann's law. Okay, now we can recap the results once more. At a given temperature, the energy is not uniformly distributed in the radiation spectrum of a black body. An increase in temperature causes an increase in the energy emission for all wavelengths. For a given temperature, intensity of radiation increases with wavelength and reaches a maximum value and then decreases. An increase in temperature causes decrease in lambda max or the dominating wavelength. So lambda max into T is a constant. This is called the Wien's displacement law. The area under each curve represents the total energy emitted by the black body at a particular temperature. The area is directly proportional to the fourth power of the temperature of the body. That is, capital E is directly proportional to T raised to 4. This represents Stefan Boltzmann's law. So my section is completed here. Next, I am handing over to Tessa.
Thank you, Anagha, and my greetings to all. So, the topics I am dealing with are Rayleigh-Jean's law and UV catastrophe. After the Wien's displacement law, here is another law which was also aimed at explaining the energy distribution in a black body radiation spectrum. It was established by Lord Rayleigh and Sir J. Jeans, over an assumption that in a blackbody radiation spectrum, the wavelength of radiation ranges from 0 to infinity. The law is basically a relation between energy distribution in a blackbody radiation spectrum and wavelength. The law is all about energy distribution, and it's given by E lambda d lambda is equal to 8 pi kb T by lambda raised to 4 d lambda, where kb is the Boltzmann's constant, which is equal to 1.38 into 10 raised to minus 23 meter squared kilogram per second squared per Kelvin. Here T is the temperature and lambda the wavelength. Where did it fail then? Yeah, just like the Wien's displacement law, Rayleigh-Jean's law was a failure too, and it was found to be wrong by Rubens and Kohlbaum. Let's discuss the shortcomings. It fails for shorter wavelengths, even if it was in agreement with the experimental results obtained by Lummer and Prince-Heim in longer wavelength region. So clearly, the law was not precisely agreeing with the experimental results. Here is a comparison between the two laws which were established to explain the energy distribution in a blackbody radiation spectrum and the experimental results. You can see that As the wavelength of the radiation decreases, according to Rayleigh-Jean's law, the energy density keeps on increasing and it's tending towards infinity. The ultraviolet catastrophe. This term has its relevance in the failure of Rayleigh-Jean's law. But before getting into the term, we have to discuss a bit more the drawbacks of the law. As we have just seen, the Rayleigh-Jean's law agrees well with the experimental results at low frequencies or longer wavelengths but shows violent disagreement at higher frequencies. Here this graph shows that it's a plot between frequency and spectral energy density, and in the direction of increasing frequency, according to Rayleigh-Jean's law, the spectral energy density keeps increasing. Now let's discuss the drawbacks in detail. The first one, according to the law, we have seen that E lambda d lambda is equal to 8 pi kt by lambda raised to 4 d lambda. On rearranging the equation and substituting lambda is equal to c by nu and d lambda is equal to c by nu squared d lambda, the equation turns to this form. dE is equal to 8 pi nu squared kbt by c cubed d nu. Clearly, the energy density is proportional to the frequency, or we can predict that it approaches infinity as the frequency or nu tends to infinity. The second drawback, at any temperature, from the law we can derive that E is equal to integral 0 to infinity 8 pi nu squared kbt by c cubed d nu. Here also the result is infinity, which is shortly against the Stefan's law. This couple of drawbacks led to the fatal objection of the law, and the discrepancy can be called the ultraviolet catastrophe. Here is a graph which gives you an idea about the UV catastrophe. It's a plot between frequency and radiated intensity. You can see that as the frequency of the radiation increases, according to Rayleigh-Jean's law, the intensity of the radiation keeps on increasing and it's tending towards the ultraviolet catastrophe. The graph also shows that the law is much disagreeing with the experimental results. The UV catastrophe was considered to be a fatal failure of classical physics, and it was then in 1900, by the beginning of 20th century, that Max Planck came up with the quantum theory. He discovered that the radiation is emitted in quanta of energy h nu, or as we have heard before, the energy is not continuous but discontinuous in the form of small sachets of energy h nu each, where nu is the frequency of the radiation. He introduced a formula too for the spectral energy density of blackbody radiation by a luck guesswork, as he himself called it, and the formula is E lambda d lambda is equal to 8 pi h by c cubed multiplied by nu cubed by e raised to h nu by kbt minus 1 d nu. Here he introduced a new constant called the Planck's constant, which is equal to 6.626 into 10 raised to minus 34 joule second. This discovery of Max Planck was a cent percentage satisfactory with the experimental results. That's why in the previous graph the experimental curve is denoted as Planck's law. This great discovery of him paved the way for a Nobel Prize to him in the year 1918. Now my friend Amala Elizabeth will be giving you a clear-cut idea on Max Planck's quantum theory and his postulates, which was a great discovery as well as a turning point in the field of physics. So thanks all. Now it's over to you, Amala.
Thank you, my dear friend. I extend my warm greetings to all. Today I'm gonna discuss about Planck's radiation law and Planck's quantum postulates. In late 19th century, a puzzle came in front of physics which was difficult to answer. This puzzle was about blackbody radiation curve. In earlier slides, we discussed what is a blackbody and what is blackbody radiation curve. When an object emits radiation due to its internal temperature, That object is called black body and the radiation is called black body radiation. Wein's displacement law, Rayleigh-Jean's law, also we discussed earlier, tried to explain this curve. But no one was able to successfully explain, and it seemed that it's not possible to explain this by classical physics. In such situation, there was a need for a revolutionary idea which could go beyond the known physics of that time and explained it. This was done by German theoretical physicist Max Planck. Not only he successfully explained blackbody radiation curve but also led to the formation of modern physics which is today known as quantum mechanics. Now we will discuss about Planck's radiation law and its postulates. In 1901, Planck was able to derive an empirical formula to explain the experimentally observed distribution of energy in the spectrum of a black body on the basis of his revolutionary hypothesis known as quantum theory heat radiation. According to this theory, the energy distribution is given by the equation E lambda d lambda is equal to 8 pi hc the whole divided by lambda raised to 5 into e raised to hc by k lambda t minus 1 into d lambda. This is Planck's radiation law. We will discuss how Planck derived this relation in succeeding presentations. This relation agrees with the experimental curves. For this, he received Nobel Prize in the year 1918. Planck deduced this formula of distribution of energy with wavelengths by using some assumptions which may be called as Planck's quantum postulates or Planck's hypothesis. So, let us discuss about those assumptions made by Planck. The first assumption was the emission of radiation is due to vibration of charged particles or electrons in the body. That is, a black body radiation chamber is filled up not only with radiation but also with simple harmonic oscillators or resonators known as Planck's oscillators or Planck's resonators. It can vibrate with all possible frequencies. Second assumption was the emission is not continuous but in discrete packets of energy called quanta. And the third one, the emitted radiation propagates in the form of waves. And the fourth one was the energy of oscillators in a black body are quantized. That is, E is equal to h nu, where h is the Planck's constant and its value is 6.625 into 10 raised to minus 34 joule per second. Nu is the frequency of radiation. This assumption is the most revolutionary in character. So, I hope you all understood this. This is all about mine. So, let us go for a recap on today's topic. First, we discussed thermal radiation, its properties. Then some useful definitions such as total emissive power or emissivity, spectral emissive power, absorptivity or absorptive power, total energy density, relative emittance, spectral energy density. Then we discussed Prevost's theory of heat exchange, application of heat radiation and uniform temperature enclosure. Then we discussed what is a black body and what is black body radiation curve, then its temperature dependence and about black body in practice, that is Ferri's black body and Wein's black body. Then we discussed about emissive power and absorptive power. Then Kirchhoff's law of radiation, its proof and applications. Then we discussed Wein's displacement law and its graph. Stefan Boltzmann law, its equation and graph, and then the distribution of energy in black body spectrum. Then we discussed Rayleigh-Jean's law, its shortcomings and the comparison between the laws. Then we discussed about the ultraviolet catastrophe, and at last the Planck's radiation law and its postulates. With that, we conclude our presentation. We assume that the presentation was comprehensive and all get few ideas about the topic. I thank each and everyone for your cooperation. Once again, thank you, Professor, for giving us such a platform. Our sincere gratitude. Thank you.